So today we're talking about doing triple integrals in cylindrical coordinates and triple integrals with spherical coordinates. And cylindrical coordinates, you remember, are a lot like polar coordinates, in that for cylindrical, the change of coordinate formulas is that r is equal to the square root of x squared plus y squared. Theta is such that tangent of theta is y divided by x. But remember, you got to be careful when you take the arctangent. You might have to add pi. Maybe you don't add pi. It's the whole thing. And z is equal to z. That's why we say cylindrical coordinates are a lot like polar coordinates, because it is polar coordinates. And you just leave the z variable alone. And if you want to convert back to rectangular coordinates, x is r times cosine theta, y is r times sine of theta, and z is equal to z. And so we're going to see a triple integral, or more than one triple integral, that makes it so that cylindrical coordinates are going to be easier to solve that 3D region than rectangular coordinates. And so we'll want to make this switch to cylindrical coordinates. The other thing you really need to know about cylindrical coordinates is that the dz, dy, dx part that we normally get in rectangular coordinates is going to be r dr d theta dz. And you could also change the order of this, right? You could also make it like r dz dr d theta or something like that. But the important part is that we pick up a little r for the same reason you pick up an r when we do double integrals in polar coordinates. So that's the deal with cylindrical. Another thing that's new is spherical coordinates. You remember this from early on in the semester. In spherical coordinates, we've got three coordinates, rho, theta, and phi. And remember that rho is the distance from the origin to the point we're talking about in space. Theta is the same theta from polar coordinates. So theta is an angle measured in the xy plane that's measured counterclockwise from the positive x-axis. And then phi is an angle that's measured away from the positive z-axis. So you need rho, theta, and phi to tell you where you are in 3D space. If you're a big fan of GPS, theta would tell you your longitude, and phi would tell you your latitude. I don't know if that's helpful or not. I don't know if you guys do that. When I was in school, they made us like look at globes, and they would name like countries, and we had to give the latitude and longitude of the country. It's like part of a test we had back when I don't know, when was I in 5th grade? That would have been 400 years ago. No, there was a point in 5th grade where I had a globe sitting on my desk and I had to take a test on latitudes and longitudes. Anyways, those are the conversion formulas. That would give you your xyz, rho, theta, phis. And we're going to need to use those. Those are going to be things you got to memorize. And this is also really important too. Whenever I have the triple integral and then the thing at the end, we have, of course, d rho, d theta, d phi, but instead of just picking up an r, this rho squared sine of phi needs to be included with every integral in spherical coordinates. And this picture is a little bit fuzzy, but it's the geometric explanation of why we need rho squared sine of phi. Because dx, dy, dz is talking about a small little volume in space. And in these spherical coordinates, this small little volume, this little box here, has a side length that's going to be delta rho, or d rho here, because it's a change in the distance away from the origin. And then this side of the box has length rho times d theta, because the thing that's changing here is theta. Theta is this angle that's measured counterclockwise in the xy plane away from the positive x-axis. And so this little amount here is a d theta, a change in theta. Oh, sorry, I was reading the wrong thing. That's actually a phi. This is what I'm concerned with right here, right now, is we've got some d theta for this side length. And notice it doesn't just depend on theta, but if the rho were a really small number, then for the same d theta, that side length would also be really small if you're like close to the origin. So it's proportional to rho as well as d theta, and it's proportional to sine of phi. Because again, if phi was a really small number and you're getting very close to the z-axis here, do you see how that side length shrinks as you get closer to the z-axis? And sine of phi shrinks as phi gets closer to 0. And then the last side length that we haven't talked about yet is rho times d phi, because what's changing here is phi, the angle away from the z-axis. And then again, because it's going to get smaller if you get closer to the origin, it gets bigger if you get farther away from the origin. So now to find the volume of the box, you multiply the three sides of the box together, and you end up picking up a rho squared sine of phi. I copied and pasted a public domain image from Google because I can't draw that. If I tried to draw that, it's not going to turn out well. So that's the best we can do. When you purchase an ice cream cone at the local shop, they hand you an ice cream with the following shape. To determine how much ice cream you received, find the volume of the region in 3D space above the xy plane bounded inside the following cone and sphere. So this is a sphere. Centered at the origin with a radius of what? 5. This is a cone. And when x is 0 and y is 0, the boundary of this cone is at z equals 0. So it's also going to pass through the origin. I'm going to try to draw some pictures here. Maybe just one picture. Here's my xy plane, here's my z-axis. So my sphere has a radius of 5. And my cone is going to look like this. All right, take the slice out of it. So, look right here. What if I want to know the place where this cone intersects my purple sphere? And it's going to, imagine a cone intersecting a sphere. It's going to intersect at a circle. The curve of intersection between those two surfaces will be a circle. What's the radius of that circle? In other words, how far is this intersection away from my z-axis? Well, what I know is that the radius of my sphere is 5. And I can make a right triangle where one side is the x-coordinate of the intersection, one side length is the y-coordinate of the intersection. Or sorry, the z-coordinate, I should say. The z-coordinate. And then based on this right triangle, I should be able to write down the Pythagorean theorem. Let's call it r squared. Remember, r is the distance from the z-axis. Plus z squared equals 25. And this equation over here is saying that 16r squared at the boundary is going to be equal to 9z squared. Or I could replace z squared with 16 over 9 r squared. Now we write r squared plus 16 over 9 r squared equals 25. R squared is like 16 over 16, and so altogether 9 over 9, I should say. 9 plus 16 is 25, so I've got 25 ninths. R squared is equal to 25. R squared is equal to 9. R equals 3. Whew. Okay, so this side length is 3. Okay. This is a right triangle, and that side length is 3. That is, the distance away from the z-axis is 3. This is 5. What's this length? What's the z-coordinate of the intersection? 4. You got a little 3, 4, 5 triangle in there. And I think I'm ready to take the integral. That's going to tell me the volume. So here's my integral. It'll be a triple integral with integrand 1, since I'm trying to take a volume. But then let's do this in spherical coordinates, because my problem is telling me we're going to switch to spherical coordinates. And when I switch to spherical coordinates, I have to write rho squared sine of phi. And then you pick the order of integration, but we'll just try d rho, d theta, d phi. I don't know. I'm just picking something. If it doesn't work, it doesn't work. We try back. We come back and try again. The only thing I need to pick out in order to specify this integral now is what's my lower bounds and what's my upper bounds. Like for my variable phi, what should be the lower bound and upper bound of phi? Remember, phi is the angle measured away from the positive z-axis. So when phi is 0, you're pointing up in the direction of the z-axis, and phi increases when we get farther away from the z-axis. And the volume we're trying to find is this volume between the cone and the sphere. So in this solid, what's the lowest value of phi? Zero. Yeah. And phi is my outside variable, so these bounds are going to be constant numbers. The lower bound will be a constant, the upper bound will be a constant. And so whenever I have phi equals 0 and I'm pointing up to my positive z-axis, I've actually got some of the solid there. And so the lower bound of phi has to include 0. What's the upper bound of phi? It's a harder question.
Isn't the arctangent of 4/3?
Yeah. Yes, it is. So right here, if you want phi, you could either do the arctangent of y over x. No, that's right, that's wrong. The arctangent of z over r. Right, because this is z, this is r, this is a right triangle. Although, wait a second. This is actually the right triangle I'm thinking of. This would be phi. And so tangent is opposite over adjacent, which would be r over z. My bad. Drawing a picture really helps think through this. I could use arctangent of r divided by z, which is, for my upper bound, going to be the arctangent of 3 divided by 4. Or alternatively, the formula we had before was arc cosine of z over rho. Because this is z, this is rho. Rho is my hypotenuse here. And cosine is adjacent over hypotenuse, so that's why it's z over rho. And that means I could get phi by typing in arc cosine of 4 over 5. That should give you the same answer. I would personally lean towards using the arc cosine of z over rho because it doesn't have the same trouble as the arctangent does. Well, maybe it's not even a big deal because r is always positive, isn't it? And rho is always positive. And so you really don't run into this issue with the phi calculation. Phi is pretty easy to figure out. The only problem with arctangent is if the numerator and the denominator is both negative, right? Or if if both of them could be negative, then you got to worry about the quadrant problem. Quadrant 1, 2, 3, 4, trying to worry about quadrants 2 and 3. But in this case, I don't have to worry about this at all because the numerator here has to be positive and the denominator here has to be positive. Z could be positive or negative, but R and rho are always positive numbers, so you don't have to worry about that. In any case, that's going to be the upper bound here. So phi goes from 0 up to the arc cosine of 4/5. What about theta? What's the lower bound on theta? 0. Upper bound 2 pi. Because this shape has radial symmetry about the z-axis, I care about the entire shape for the entire rotation around the z-axis. And so that theta angle, that's telling me, okay, in the xy plane, let's measure an angle counterclockwise from the positive x-axis. That's going to give me the whole cone if I rotate all the way from 0 to 2 pi radians. Rho, what should be my lower bound on rho? Rho is the distance from the origin. 0 up to 5. Yeah, the upper bound on my distance from the origin for the solid is 5. Right? The lower bound is 0 and the upper bound is 5 to get the whole sphere. Sphere with radius 5. So hopefully this isn't going to be too bad when we integrate. And let's see what we get. We have some phis in here. I don't have any thetas in there. You notice how there's no thetas at all? There's no thetas in the integrand or the bounds. So that means I can write 2 pi out here. It's a little shortcut I learned. Because anything you can do to make these problems a little bit shorter is nice. And then the middle integral is going to be the antiderivative of rho squared sine of phi with respect to rho. So in other words, sine of phi is just a constant. And then I've got to take the antiderivative of rho squared. What's the antiderivative of rho squared? 1/3 rho cubed. The lower bound on rho is 0, the upper bound on rho is 5. So if I plug in the 0, I just get zeros. If I plug in the 5, I get 125 times 2 is 250 divided by 3 times pi times this. What's the antiderivative of sine? Negative cosine. Lower bound 0, upper bound arc cosine of 4/5. So I get 250 divided by 3 times pi times negative 4/5. minus negative 1, which is 250 thirds pi times 1 minus 4/5, so that's 1/5. 250 divided by 5 is 50, so it's 50 thirds pi. That's my volume.
Dr. Moffat, how did you know to shade in that particular region when you had the graph?
It's a good question.
Like rather than like the two like smaller like triangle-ish shapes below the cone.
Mm-hmm. So these inequalities are telling me, okay, sphere, but the x, the y, and the z, in other words, the rho squared. Here, let me just convert that for you. This inequality is telling me that rho has to be less than 5. So for my solid, the distance from the origin has to be less than 5. So I know it's going to be inside the purple circle, and I guess you knew that too. Really, the question is then about this green cone. We're like wondering what direction is that inequality looking? And I guess it's really about this. Is that I would write 16r squared is less than or equal to 9z squared. Or I would say that divide both sides by 9 and z squared should be greater than or equal to 16 over 9 r squared. So this is saying that if this is my r and this is my z, the z can be greater than or equal to the r, right? With some scale factor, this 16 over 9 is basically telling me the slope of this green line here. But the direction of this inequality saying that the z part should be greater than the r part is telling me that it's okay to be up above this green line where the z's are larger, but it's not okay to be below the green line where the r's are larger. It's a good question. Other questions? Okay. All right. This example is the same question, only this time we're going to solve the same integral in cylindrical coordinates. So cylindrical coordinates means my integrand is just going to be r dr d theta dz. Maybe I don't like that order of integration. I mean, you can try it. And if your order of integration doesn't work for you, you can always try something else. But let's try this. See how it goes. Theta. What's the lower bound on theta? We already did this. It's 0 to 2 pi. Right? Theta is the same theta as the previous problem. And so we're still concerned with the full rotation of the cone. We're still concerned with the whole 0 to 2 pi range of this theta. R is no longer the distance from the origin, but it's the distance from the z-axis. So let's look at our picture again. what's the lower bound in this yellow solid from for the distance from the z-axis? The lower bound on r is 0. Yeah, because I have part of my solid touching the z-axis. So the lower bound on r is 0. What's the upper bound on r?
3.
Well, the upper bound on r is kind of given by this green line. But if I were trying to describe the upper bound on r with this green line is just a function of z and r. So if I were trying to express that as an upper bound, I would end up being a function of z. But I don't want to mention that z variable. I don't want to mention the z variable here because z's on the inside. And so we can't mention any z's in my bounds on r because otherwise it wouldn't get removed by integration. So we're not gonna worry about this. What about in purple? In purple, the sphere has the equation x squared plus y squared plus z squared is equal to 25, which is like saying r squared plus z squared is equal to 25, which again, if I were going to try to represent this part of the sphere as an upper bound on r, it would have to be a function of z. I don't want it to be a function of z. And so instead, I'm just going to choose a constant upper bound of r, which is 3. So my upper bound on r is going to be 3. And instead, I'm going to try to represent the cone and the purple sphere using the lower bound and the upper bound on my z variable. So that way I get the right shape. So for my z variable, for this yellow shaded region, the lower bound of the z variable is the green cone. Yeah, in the yellow region, the lower bound on the z variable is this green cone. So in other words, I'm going to set my lower bound on z equal to 4/3 r. Because I'll just look at that equation, I'll take the square root of both sides and say z has to be greater than or equal to 4/3r. The upper bound on z is the purple sphere, and that means that z has to be less than or equal to the square root of 25 minus r squared. So my upper bound on my z integral is going to be the square root of 25 minus r squared. So again, theta gets to go from 0 to 2 pi because that's the full rotation. The r gets to go from 0 to 3. And those are constants because we didn't want to mention the z variable because the z variable is on the inside. And then for my z variable, the 4/3 r represents the cone on the bottom. And then the square root of 25 minus r squared represents the sphere on the top. Does everybody follow so far? Do you need me to scroll up and look at the picture? Yeah, you're good? Okay. So then we're ready to integrate. We just have to do this one step at a time. Once again, we notice since there are no thetas in the integrand, and no thetas in the bounds, then we just multiply by 2 pi. And then I have the integral from 0 to 3. I can't make that one go away because there is an r in both the integrand and the bounds. But I can pull the r outside of this integral from 4/3 r to square root of 25 minus r squared of 1 dz dr. What's the antiderivative of 1 with respect to z? Z. So this is going to be r times the square root of 25 minus r squared minus 4/3 r squared dr. And I think it would be easier to treat these separately, which means I'm going to have one integral be eventually solved with u substitution. And then the other integral be a lot easier. It's negative 4/3 times r squared dr. What should I choose for u over here? It's 25 minus r squared. So there's going to be a negative half. And then I'm going to replace r dr with du. So the square root of u du. 0 is going to be 25 minus 0 squared, so 25 for my lower bound. And then 3 is going to be 25 minus 3 squared, which is going to be 16 for the upper bound. The negative half times the 2 makes it negative pi. Although I could make it positive pi if I just switch the bounds. And then u to the half du. What's the antiderivative of u to the half? Antiderivative of u to the half power is going to be u to the 3/2 power times 2/3. And then 25 to the 3/2 power is going to be 125. 125 times 2 is going to be 250 over 3 pi minus 16 to the 3/2 power is going to be 64. 64 times 2 is 128 thirds pi. So now I'm going to recombine these results and get like, okay, 250 minus 128 minus, what's 24 times 3? 72? (50 thirds pi), which is great because this is the same problem we worked a moment ago in spherical coordinates. And we hoped to get the same answer even if we choose to work this out in cylindrical coordinates. And that's the same answer. Where's Ben today? I was going to ask him what's bigger, a quarter pounder or a third of a pound hamburger? Which is bigger, Alex? A quarter pounder or like a third of a pound? A third pounder? 4 is a bigger number than 3, though. It's an important lesson to teach to Ben's 7th graders. Okay. What else? There's some of these questions on the homework under exercise 3 that say, when you purchase an ice cream cone at the local shop, they hand you an ice cream with the following shape. Oh, look, it's the same question. These are long questions, so I keep them the same. There's not like, this lecture would take way too long if I was going to choose 3 different shapes. At least we're already familiar with this shape. But what if I wanted to know the center of mass of this solid? You could ask ChatGPT. Find the center of mass of the solid occupying the region in 3D space above the xy plane bounded inside the cone and sphere. Assume it has a uniform density. So, center of mass is a little bit tricky. You know, we've got we've got this sphere and this cone in this shape. So feel free to use your brain. Let me say that again. Feel free to think about the shape in kind of just a geometric sense, just like common sense reasoning. What are the symmetries here? I don't want to do more work than I have to. I'm not going to whip out the formulas where you have to use like a triple integral of x times rho and a triple integral of y times rho and a triple integral with z times rho to find the x and the y and the z and blah, blah, blah. Because this, despite how poorly and lopsided I drew this, this is supposed to be symmetric. It's supposed to have radial symmetry about the z-axis. So if this has uniform density, which it does, is the center of mass going to be on the z-axis? Yes. So I don't have to worry about the x-coordinate. I don't have to worry about the y-coordinate for my center of mass. I know those will both be 0 just from common sense reasoning here. Okay, so the x-coordinate of the center of mass, 0. The y-coordinate of the center of mass, 0. The z-coordinate of the center of mass has the formula z times rho, whatever. And so I would like to keep cylindrical coordinates instead of trying to do rectangular coordinates. So let's keep the same cylindrical coordinate triple integral that we had in the previous problem. And since it has uniform density, rho is just a constant, right? It doesn't depend on x, y, and z. Rho is a constant for uniform density. So forget about rho. You could say rho is out here because it's a constant. The last problem, when we did this with cylindrical coordinates, had us do this. We're just going to copy this integral. Only now we're including a z in the integrand. So we're looking at the integral from 0 to 2 pi, of the integral from 0 to 3, of the integral from 4/3 r to the square root of 25 minus r squared, of zr dz dr d theta. Okay, does everybody see how we set this problem up? And a lot of the problems in exercise 3 on your homework also have radial symmetry, right? You also share the idea that you don't have to find x bar, you don't have to find y bar. Those are going to be on the z-axis. You just got to find the z-coordinate. So don't do more work than you have to. Okay, this integral then is going to be, again, no thetas, right? There's no thetas in the balance, there's no thetas in the integrand, so let's just multiply times 2 pi. We can get rid of the outside integral. And instead we've got the integral from 0 to 3 r, integral from 4/3 r to square root 25 minus r squared, z dz dr. So it's going to have rho times 2 pi times integral from 0 to 3 r. The antiderivative of z is 1/2 z squared. So there's rho times 2 times pi. You know what? I forgot about something. What did I forget? I'll give you a hint. It goes right here. 1 over m. Thank you. I forgot about the mass. Okay. Something was bothering me, and I found out what it was. This formula should really have 1 over the mass times the triple integral of all the junk. Okay, well, what is mass? Mass is rho times volume. Density times volume equals mass. That's true because we have uniform density. I wouldn't have to say that if we didn't have uniform density, but in this case, since it's uniform throughout the whole volume, the mass is going to be the density times the volume. So when I have 1 over m, I'm going to get rho divided by rho times volume. So what has been bothering me this entire time is I was like, why do we have a rho here? I feel like it shouldn't be a rho. I feel like it should be divided by volume. There we go. Because these two rows are going to cancel. I'm glad we fixed that. Okay, now we're back to our integral where we were working from 0 to 3 of yuck. It's, I'm taking out the half, so ignore the half. Then if I'm going to take the square root and then square it, that stuff's going to cancel. And I'm going to get r times 25 minus r cubed minus 4/3 r is about to be squared, so it's going to be 16/9 r squared times r. So 16/9 r cubed. The 2 and the 1/2 are going to cancel, and I get pi over the volume. We know the volume, by the way. We already found that the volume was 50/3 pi. So dividing by the volume is going to be dividing by 50/3 pi. So those pi's are going to cancel in the next step. And then we got to take the antiderivative of 25r, which is going to be 25 over 2r squared. And then we've got to take minus 25/9 r cubed, and then take the antiderivative. So it's going to be like minus 25 over 36. You guys got to double check me and make sure I'm doing this right. The pi's cancel, and we get 3 over 50 times, the zeros would give me 0. The 3's would give me 25 times 9 over 2 minus 25 times 9 over 4. Because I got 3 to the 4th power. 36 has a 9 factor in there somewhere. So I'm just imagining multiplying 25 by 9 and then 36 divided by 9 to get rid of the r to the 4th. So I'm going to be left with 25 times 9, 3 over 50 times 25 times 9 over 4 when I subtract. So the 25 and the 50 make 1/2. The 9 times 3 makes 27. So it's going to be 27/8. And that's the z coordinate for my center of mass. 27/8, that's a little bit more than 3. 24/8 would be 3, so 27/8 is like 3.375. Let's see where that would be, because remember anytime you do a center of mass problem, it's really easy to check your answer. Just plot, this is 5, so 1, 2, 3, 4, 5. I just found that my center of mass should be at 3 and 3.75, right? That's my center of mass. Does that seem reasonable, the location for my center of mass? Yeah. If I found something that was outside of my solid, like something that was too high on my z-axis or too low on my z-axis or something, that would be a little bit concerning, but that's right there in the middle, and so I think that's true. So I think my center of mass that we're looking for has coordinates 0, 0, 3.375. Right? 27/8. So that's it. Did you have questions about that problem? You excited for your test Thursday?
Excited. It's a word to use.
Just don't be like me. Don't forget to divide by your mass when finding center of mass. You'd get a way different. You would know, if I continued like that, I forgot to divide by the mass, I would find an answer that was like way up high on my z-axis, and I'd be like, oh man, I got the problem wrong. I checked my answer, it doesn't work, and then I would have to eventually go back and remember. But